Hi everyone, my name is Nicola Dreolin, and in this video I'm going to talk about how the fundamental low field eye mobility equation, also called Mason-Champ equation, is affected by the measurement uncertainty. But first of all, I'm going to spend a few words on traveling wave and drift tube devices that we can find on the market today. And if you have seen my previous videos, you know that I work as a scientist for Waters Corporation, a company that also manufactures traveling wave devices. So I might be a little biased when talking about IMS, but I will do my best, as always, to go through the topics impartially and scientifically with no marketing purposes. I will use the results of some recent comprehensive interlaboratory exercises done on drift tube eye mobility to explain the concepts of measurement uncertainty when we use the fundamental low field IMS equation in the step field methods. And finally, I will also discuss how to measure or not the accuracy or trueness of CCS values and also the precision of CCS, which we know are two different concepts. In the previous video, in the previous videos, I referred a lot to the Synapse system. And here I report a scheme that is also available at waters.com, highlighting the main components, starting from the ion source down to the extended TOF. This is the latest version, the Synapse XS, which has been launched last year, and this is the top performance of its category, and it was born from the Synapse G2SI. The Synapse is quite a peculiar system because, to my knowledge, is the only commercially available instrument that is able to measure the drift time and derive the CCS of the precursor ions, as well as the CCS of fragment ions. This is because it holds the ion mobility cell after the quadruple mass filter and between the trap and the transfer regions, which can both act either as a collision cell or as ion guide. The helium cell function is to cool down the ions coming from the trap before entering the IMS cell, and whose principle of operation is obviously the traveling wave technology. The Vion IMS QTOF is a commercial traveling wave ion mobility system, still from Waters, which mainly differs by the location of the mobility cell in the ion path, that is before the quadrupole. But when we look at commercial systems with a drift tube ion mobility, in analogy to the Vion, we have the 6560 ion mobility LCQ TOF from Agilent Technologies, which has been launched in 2013, and they both are big guys, and the 6560 is very long. It takes almost 3 meters of bench space. In both systems, the ion mobility cell is located before the quadrupole, as I said before, and in the Vion, the step wave stacked ring ion guide acts has an interface between the ambient ionization region and the low pressure region. Before the mobility cell, we have a trap, which enables the transmission of discrete packets of ions through the IMS. The way CCS are derived on the Vion is fundamentally different from the Synapse. In the Synapse, because the mobility cell is located far away from the ambient pressure region, the buffer gas flow is fixed and the gas pressure does not fluctuate significantly. And so the calibration function is applied and a reference analyte with a known CCS is directly infused throughout the analysis, usually leucine and kephalin, and it is used to determine a correction factor that enables the derivation of CCS of unknown compounds, the so-called log CCS function. On the Vion instead, the geometry is different and any changes in pressure in the source region of the instrument due to, for example, different LC flow rates or different composition can cause a corresponding change in the trap and IMS pressure. In order to prevent this pressure effect occurring in the Vion IMS QTOF, A real-time feedback loop has been implemented where the trap and ion mobility pressure are continuously measured, and any changes in the pressure are compensated for by adjusting the nitrogen flow rate delivered by the trap and ion flow controllers. In this way, the CCS correction factor is not needed on the Vion, and the calibration function is applied directly. In the 6560, the front funnel operates at high pressures. The key function of the front ion funnel, likewise the step wave in the Vion, is to enrich the sample ions and remove excess gas. Also here, the continuous ion beam from the electrospray has to be converted into a pulsed ion beam prior to the ion mobility separation. The trapping funnel operates similarly to the trap by first storing and then releasing the packets of ions into the drift tube. And ions then undergo ion mobility separation and are refocused by the rear funnel before entering the hexapole ion guide, quadrupole, collision cell, and then the TOF. And these two systems have pretty much similar performance according to the specs. IMS resolving power is 60 for the 6560, whilst for the Vion is about 40. Although resolving power is a relative concept because for a direct comparison, we should infuse exactly the same standard and calculate the peak width at half height or at 10% height. The main advantage that Agilent claims over its competitors is that drift tube ion mobility is the gold standard for CCS measurements. This is because CCS values can be directly derived from drift time measurements using the primary method that I described in the previous video, and which make use of the fundamental low field ion mobility equation. Whereas in the traveling wave, so far this is not possible and a calibration is required. Waters currently uses the measure mix for the calibration of commercial traveling wave instruments, which is a mix containing polyethylene, and a number of additional small molecules, which include perfluorinated compounds in the range of 1000, 2000 mass to charge, and some organic acids. For the 6560, the Agilent tube mix is used for mass and CCS calibration for the single field method, and which includes a mix of hexakis fluoropropoxy phosphazenes. Whereas for the step field method, the commercial 6560 IMS system generates CCS values with the fundamental low field ion mobility equations and uses a calibration factor, and this factor is a correction factor that is obtained by the analysis in step field of a reference analyte with mass to charge of 922.0126 and a CCS of 243 Armstrong squared. This is because in practice, the control and measurement of actual pressure and temperature among the other factors appearing in the equation is not easy, and therefore also in the step field method, commercial systems need to use a correction parameter. Otherwise, a significant deviation will affect the experimental values. However, if we introduce a calibration or correction factor, we are not performing a direct measurement anymore. And it is like a one-point calibration, and we cannot consider the step field approach as a real primary method in my view, but this is open to discussion. The scientific article introducing the commercial drift tube for the first time was published in 2014, and here the authors created a database of 594 CCS values in nitrogen for analytes belonging to different chemical classes, such as ammonium salts, lipids, peptides, and carbohydrates, with a precision calculated in terms of percentage relative standard deviation of below 0.5%. They also stated in the text that on the basis of the propagation of errors analysis, incorporating the limits of precision for individual experimental parameters, we estimate the accuracy of all CCS values to be better than 2%. Okay, if we consider the propagation of errors equation, we can calculate the combined standard uncertainty, mu c, for the reduced mobility K0 and also for the CCS, with the formula here, using the propagation of the standard uncertainty mu of each component of the fundamental low field ion mobility equation. The variables are drift tube length, temperature, pressure, reduced mass, charge, and the slope of a linear regression. The contribution of the uncertainties of the temperature and the pressure usually dominate the combined uncertainty of the reduced mobility. If we know exactly the mass and charge of the analyte, then their respective uncertainties are zero in the formula of mu c for the CCS, although the gas purity is affecting the uncertainty associated with the reduced mobility because traces of other gases can contribute to its uncertainty. And if we take a look at their supplemental material, we find that, according to the authors, individual CCS measurements which contributed to a percentage relative standard deviation beyond 0.5% were generally found to be indicative of a poor centroid fit and ultimately were not included in the dataset reported in the manuscript. So they have excluded some data before the statistical treatment, apparently for a general criteria of low ion counting or multiple peaks features. The 2% of before is given by the sum of 0.5% and 1.5%. The first term is the uncertainty from replicate measurements, whilst the second term is the contribution of the combined uncertainty of the CCS calculated with the formula shown in the previous slide, which means the uncertainty coming from the intrinsic error in measuring the actual temperature, pressure, drift voltage, etc. So what I call measurement uncertainty. They also say that in the worst case scenario, which sees the smallest ion with mass over m over z 186 at the highest field of 20 volt per centimeter, the field induced ion temperature is about 3 Kelvin greater than the drift gas temperature. This means that the measurement, or better said, the estimation of the effective temperature experienced by the ion can bring about an additional error of up to 0.5%. And this was neglected in the calculation of the combined uncertainty. The same authors published a second work in 2017 where they conducted an interlaboratory study to evaluate the reproducibility of CCS from 4 laboratories using the 6560. One of the systems, located in Agilent headquarters at Santa Clara, was kept as reference system, which we can see in this slide, and was modified in a way that drift tube length, temperature, pressure, and voltage could be monitored with higher precision. They stated that the CCS values derived with this reference system were the best estimate of the true value and were used to determine the bias of CCS for the other 3 commercial drift tube instruments. They achieved very good results and used the step field CCS values of the tube mix for calculating the for calibrating, the system, and derived the CCS also using the single field method via linear regression. They centered this paper on the theoretical estimation of expanded uncertainty of drift tube measurements and utilized the Monte Carlo simulations to obtain a normal distribution of drift time measurements and therefore an expanded uncertainty and relative uncertainty, and confirmed that drift gas pressure and temperature are the primary input quantities which contribute to the uncertainty in the IMS measurements, with a contribution of over 40% each. There is a problem though. They calculated an average bias to the reference system of 0.34% for a step field and 0.54% for a single field. And the average interlaboratory relative standard deviation was 0.29%. And speaking in terms of relative standard deviation under repeatability and reproducibility conditions is correct, as it is a measure of precision. However, when we calculate the bias, that is a percentage difference between two values, we need to be careful in defining what the reference values actually represent. The authors use the values of the reference system with the step field as the true value, assumed to be the closest to the theoretical real CCS values, because it presents the highest precision in controlling and measuring the parameters affecting the Mason-Champ equation, so pressure, temperature, electric field, and length. In this way, they use the bias as a measure of accuracy. The problem is that the instrumental, also called experimental uncertainty, is not the only factor affecting the total bias to the theoretical real value. We also have the uncertainty coming from the assumptions embedded into the fundamental low field immobility equation itself that we have seen in the first video. And at some point, the authors admitted this under the lines with this sentence. We have seen in the first video that a number of assumptions are embedded into the fundamental low field immobility equation, also known as the Mason-Champ equation. The relation of proportionality between the drift velocity and the electric field is only valid at weak electric fields, and it is not presently clear what exactly weak means. Only binary collisions between ions and buffer gas are important, and multiple collisions do not occur. Ions and neutrals collide like rigid spheres, and therefore only elastic collisions occur, and for inelastic collisions some modification are needed. The center of force is equivalent with the center of mass, and it is clear that this is not the case for many molecules, especially for the big molecules. Buffer gas molecules have negligible dipole or quadrupole moments, and we know that this is not the case for nitrogen, for example. And finally, K is only the first approximation of the mobility constant, and improvements amount to up to 2% for ions whose masses are equal to or greater than the mass of the neutral molecule. All these factors contribute to the overall estimation uncertainty when using the Mason-Champ equation in the step field method with the drift tube. To the estimation uncertainty, we have to add the uncertainty related to the measurement of experimental parameters such as the buffer gas temperature. The temperature measurements made outside and inside the drift region, taken with the most sophisticated thermocouple, can be different from the effective temperature experienced by the ions. In fact, the temperature is one of the most difficult parameters to control and measure, and it is a major source of bias and fluctuations. A bias is introduced also when there are fluctuations of drift voltage. Those potential difference which will produce an uneven electric field. And in addition, the voltage probes used to monitor the delta voltage can alter the observed potential in the drift region. And the number of density of the buffer gas also enters into the fundamental low field equation. N is the number of gas molecules in a given volume of gas, and depends on the pressure and temperature. This means that also the fine measurement of pressure is essential to reduce the instrumental or experimental bias. Differences between geometric lengths of the drift tube from lab to lab, the effective length over which the potential difference is applied, and gas dynamics are also contributing to the experimental bias. The effective length may depend on delta V and on the field in the optics entering and exiting the drift tube. And finally, the mass of the buffer gas is also present in the equation, particularly in the reduced mass mu. In theory, if we work under 100% helium, for example, the mass of the gas is well known, although we need to consider the gas purity, which affects the mass of the gas. In addition, pressure homogeneity and the absence of net gas flow is often assumed, but is difficult to achieve in practice. And all these factors contribute to the overall measurement uncertainty, the uncertainty associated to the errors in measuring experimental parameters affecting the fundamental low field IMS equation. The sum of estimation uncertainty and measurement uncertainty will give the total bias in CCS derivation. Interestingly, when using a secondary method that employs a calibration curve, such as a single field rather than the step field on a drift tube, we decrease the contribution of measurement uncertainty tending to zero, because as long as we use exactly the same condition compared to the calibration, the experimental parameters such as temperature, pressure, etc. do not enter in the calculation for the derivation of CCS. The problem is basically the problem of secondary methods is the trueness of the reference CCS used for the calibration, because we are deriving experimental values using others' experimental values as reference. In other words, the problem of secondary methods is the primary method itself. This is because we need to bear very well in mind that the fundamental low field ion mobility equation is still a model. It does not represent an absolute relation between two quantities, as it holds a number of assumptions and approximation with physical meaning. And for this reason, we cannot talk in terms of accuracy of CCS, because the true or theoretical value is not known. But we can refer to deviations when we compare different CCS values between platform and different technologies. What we can do is attempting to reach greater precision in order to use CCS more confidently in many applications. Or we can compare CCS values to determine the deviations and try to understand why these deviations occur. We can see if they are comparable with instrumental reproducibility, therefore if we are within the precision threshold, or if they are significantly higher, thus driving the attention towards fundamental differences between two experiments. But again, using the term accuracy is incorrect in this context, and we can use the term deviations if we compare different technologies to reference values, or we can speak in terms of precision. And going back to the initial discussion about primary and secondary methods, I would like to repropose the words of Professor Matt Bush, that at the IMS Great Minds Summit said that for high resolution mass spectrometry, we will never dream of determining the mass to charge ratio of an ion from first principle by deriving the mass to charge from the formula of the time of flight, considering the length of a flight tube and the voltage applied. Instead, we use standards with known mass and charge, and we calibrate our instrument on those standards. In this way, we make sure that measurements performed on different platforms or by different people at different points in time are all directly comparable to each other. The same principle can be applied to CCS values. Unfortunately, unlike the monoisotopic mass and charge of standard, the theoretical CCS value is not known, and we are forced to use experimental CCS from the drift tube as a reference to calibrate and derive others' experimental values. And this is fundamentally the drawback, the limitation of ion mobility as it stands today compared to mass spectrometry, for example. With this last slide, I want to summarize the key points that we have treated in this video, which are mainly two. We have seen that the fundamental low field ion mobility equation is a model affected by a bias given by the estimation uncertainty and also the measurement uncertainty. Moreover, absolute, true, or theoretical CCS values are not known, and for this reason the terms accuracy or error of CCS are not correct. We can calculate the precision of our measurements, or we can calculate the deviations of our measurements compared to different experimentally derived values. Thank you for watching, and in the next video I will discuss the possibility or not to build a universal CCS database extendable to all technologies. I will talk about the limitations of currently available commercial IMS system in the derivation of CCS, and I will provide some personal views on the future prospects of IMS. Like always, feel free to comment and let me know your ideas, or if you have any suggestions, they are more than welcome. You can find me on LinkedIn and on ResearchGate. Ciao.